The order product is responsible the drop in size as compared with square root cancellation. So I've told you we're going to have a drop in size here as well. So maybe the order product is going to be a useful thing to have around. Yes. Here. So I said here. So the size at the first moment is smaller than you would expect just from square root cancellation. The reason it's smaller is because this thing doesn't behave like this sum, it behaves like the order product instead. The order product doesn't converge, but it still governs the size, despite not converging. So it requires a lot of work to see that it still governs the size, but heuristically that's why this is the size. If you pretend that this is like a random order product, this is the answer you get. If you pretend it's like a random sum, this is the answer you would get, which is wrong. Okay. Other questions? Right. So I want to get the order product into play. How can I do it? So the obvious way is to use prom. Okay, so f of n is like 1 over 2 pi I, the integral up a line and f is a finite product, so I can have any positive abscissa if I want to. But this won't work, so why not? So this is this is inefficient. Well, first of all, I have this 1/s around, which isn't very good, because I'm probably going to end up putting some absolute values inside the integral at some point, and then I'll have something like integral 1/mod s, which diverges logarithmically and that's a disaster, because I'm trying to wing square root log x at most, so if I lose a log, I'm done. Now you could fix this if you were happy with having a smoothly cut sum instead of a sharp cut-off here, which you might be. But then there's a much worse problem, so first of all that diverges logarithmically. Also, we would need to get cancellation from the oscillations of f of s times x to the it, which is generally very hard. Okay, so if I took c to be 1/2, which is the most natural choice, then I'd have an x to the 1/2 here, which would